This is week 6, and on week 6, we're going to talk about something that is absolutely critical to the study of chemistry, and that is the periodic table. In order to understand the periodic table, one must understand the distribution of electrons and how that distribution affects the chemical properties of various substances and elements. And so we'll start this discussion about the periodic table by starting to talk about how electrons are arranged around the atoms. First of all, the outermost electrons, you'll remember last week we talked about electron shells, and in every case, in every atom, there's going to be an outside shell where there are some electrons that hang out. And these outermost electrons are called valence electrons because they reside in the valence shell. These electrons are important because they are the ones that take part in an exchange or in some sharing or are gained or lost in chemical reactions and chemical compounds. Now, the electrons, when they are exchanged, they try to achieve what is known as the rule of octet. Now, as with any rule, there are exceptions. However, in well over 90% of all cases, the rule of octet will be obeyed. And that rule says that most atoms tend to react, that is, exchange electrons in such a way as to attain 8 electrons in the valence shell, in the outermost shell. Now, obviously, with an element like hydrogen, which has its outermost shell can only contain 2 electrons, this octet rule doesn't apply. But in virtually all other atoms, the attempt that's being done by every atom that's involved is to try to get 8 electrons in its valence shell. So for example, you see here you have chlorine, which has 7 electrons in its valence shell, and you can count the 7 blue dots on the left. It reacts with hydrogen, which has 1 red dot. And you'll notice that there's an exchange of electrons here on the right in such a way that chlorine now has 8 electrons. But also, at the same time, hydrogen can borrow an electron from chlorine and have 2 in its outer shell, which is good for hydrogen, and it's the only element other than helium that's good for. Or hydrogen can be left as an ion without any electrons in its outer shell. When we talk about the periodic table, we have to talk about exactly how the periodic table was developed. And what the periodic table is a means of organizing and remembering a large number of elements and their properties. The periodic table is such a valuable instrument because without having to measure or memorize things about 50, 60, 70, 80 different elements, you can look at the periodic table and determine by where it resides on the table and so forth many aspects of its chemical properties. Now, initially, elements were grouped together. This was over 100 years ago, in something known as triads. And triads were groupings of 3 that were based on similar properties. Now, fairly quickly, as time passed, it was found that these triads just didn't work in terms of prediction. And however, there was noted what was called periodicity. And what periodicity means is that there's a repetition of certain properties at regular intervals. It's sort of like in music, every 8 notes, it represents a scale, and then the next note is related to the note that is 8 notes down from it in a certain way. Similarly, it was found that there were elements that were related to each other in properties in regular intervals. And initially, it was attempted to place the elements in terms of their atomic mass. Regrettably, that didn't work either. So what ended up happening was that they decided to arrange the elements in terms of atomic number, but before that happened, they had what was known as the rule of octaves, and as you know, the music scale is occurs in sections of 8, and similarly, what they tried to do was when they arranged elements in according to their atomic mass, they said that every 8th element had properties similar to the one that was 8 steps down from it. As it turned out, that didn't work out, as I said before, and they had to arrange the elements in terms of atomic number. Once they arranged the elements in terms of atomic number, they developed what was known as the periodic law, which states that the property of elements repeat in specific repeating periods, and it turns out that if you arrange elements in terms of their atomic number, this works out quite well. And that's what I say right here. The important change here is to list the elements in order of their atomic number as opposed to their atomic mass. So the periodic law of elements states that the property of elements vary with the atomic number in a repeating or periodic way. So when they did that, they were able to arrange the elements in what was known as classes. And classes are the columns that you see on the periodic table. It would probably be a good idea at this point, if you don't already have the periodic table in front of you, to look up a periodic table in your book and have that in front of you while we talk about these various classes of elements. So if you don't have one in front of you, stop the video at this point and get your book or look up a periodic table on Google so that you have one that you can look at while we're talking. So the first way to classify elements was to classify them in terms of metals, nonmetals, and what was known as metalloids or semimetals. Metals were elements that have few valence electrons, generally 1, 2, or 3 valence electrons. They have certain properties such as malleability, or they're malleable, which means they can be bent without breaking. They're ductile, which means that they can be stretched into strings without breaking, or wires. They conduct both heat and electricity. Nonmetals, on the other hand, have more valence electrons, usually 5, 6, 7 valence electrons. They do not conduct heat and will not conduct electricity. Metalloids are somewhere between nonmetals and metals in terms of their properties, and they're also sometimes called semi. Another way to group or to look at classes is to put them in columns known as groups. These columns are also sometimes called families of elements. For example, the first column on the left of your periodic table, it has a 1A at the top of the column. This is called the alkali metal group. They all have one valence electron. That valence electron is easily lost. The metals tend to be very reactive and soft. The second group is called the alkaline earth metals. It has a 2A, or Roman numeral 2, and an A above the group. They all have 2 valence electrons. These tend to be more stable than 1A elements, but have very similar properties other than their increased stability. So here is an example of a periodic table. And first of all, we were talking about this line, which is called the line of separation. It separates the metals, which are over here in green, from the nonmetals, which are over here in, I guess that's red. Now, as it turns out, hydrogen is also a nonmetal, just happens to be over here, and it's sort of the outlier. Now, the metalloids, or semimetals, they all touch this line, and they're yellow on this side of the line and on this side of the line. So, like I said, you don't have to remember any particular element, whether it's a metal or not. You just look at where it is on the table, and you say, well, chromium's here, so it's a metal. Phosphorus is over here, so it's a nonmetal. And so by understanding this relationship in the periodic table, it helps you understand what properties these various elements might have. Now here is a more sophisticated looking periodic table. And here are the groups I was talking about. Here's the 1A group, which is the alkali metals. Notice I said it had a 1A at the top. The 2A group, which is the alkaline earth metals. All of these alkali metals have one electron in their valence shell. They all have fairly low electronegativity, which means they lose their electrons quite easily. And all of them tend to react the same way, generally the same way. These are the alkaline earth metals, and they have two valence electrons. And then we're going to talk about other families over here. These are the halogens, these are the calogens, and so forth. These are the noble gases here, and we'll talk about those in just a minute. Now in between, if we go back here, the elements in between from here over to here, so this whole area right in here, which is also this area right in here, those are known as transition elements or transition metals. They all have a B instead of an A, and they all have generally one or two valence electrons, and they all have very similar reactive properties. The boron family, again, if you have your table in front of you, you can look at that. The group 3A, boron itself is a metalloid, but the others are metals. And aluminum, and all of these have three valence electrons, and aluminum is the most common that has three valence electrons. The carbon family, 4, has 4 valence electrons. And the important thing about the fact that it has 4 valence electrons is that carbon is extremely versatile in terms of its ability to bind and react, which is why it is in the center of almost all of biochemistry and almost all of organic chemistry, because carbon will react in so many different ways and so many different compounds. It has its own chemistry, which is called organic chemistry. The nitrogen family has 5 valence electrons. Nitrogen is the most common gas in air. The oxygen family, also known as the calogens, the 6A have 6 valence electrons. And then the halogens, chlorine, bromine, iodine, fluorine, they have 7 valence electrons. These have a very high electronegativity, and they keep their electrons, and they tend to snatch electrons from other elements. And then the noble gases, the last column on the right, they are inert because they've already fulfilled the rule of octet, so they do not react with other substances. Their outer shell is filled. And that's one of the reasons they're called noble gases. They're thought to be, quote unquote, arrogant or noble. They won't interact with other substances.